Welcome, dear learner. Let us understand how to determine numerical aperture and acceptance angle of an optical fiber experimentally in this video. Before going into the experimental procedure, let us glimpse what an optical fiber is. Low loss is arguably the most important characteristic for a transmission media for any signal communication. Attenuation of electrical signals over the conventional cables is very high. Thus, light was used as a tool to explore in many fields. Here is one such example of primitive light carrying pipe that was used as a light source for surgeries during 1940s to generate the sterile beams devoid of heat, glare or electric shock. These instruments are molded from a transparent plastic which carries light around bends and curves. In the 1960s, Charles Keogh made an unprecedented work in this field by using a fiber of very pure glass that transported sufficient light, which is shown here as a seminal paper. It was the birth of an optical fiber. Today, with the advent of laser technology, his solution has made telecommunications using optical fibers possible. For this invention, Keogh has been conferred in 2009 Nobel Prize in Physics. Now let us learn some of the important parameters of such a modern marvel known as optical fiber. Objective of this experiment is to determine the numerical aperture and the acceptance angle of the given optical fiber. And the learning outcomes are: understand the concept of light gathering capacity of given optical fiber, distinguish the acceptance angle and acceptance cone, and realize the phenomena of total internal reflection. The apparatus required are an optical fiber. Here it is 1 meter in length. Numerical aperture measuring jig. This is the jig, which has concentric circles with 5 mm diameter for the first interior circle, 10 mm diameter for the next circle, 15 mm and 20 mm for the third and fourth consecutive circles from the center. That means each circle varies by 5 mm. The scale. This is a normal linear scale with minimum measuring distance of 1 mm. A fiber optic trainer module, which acts as a light source in this experiment. Numerical aperture for an optical fiber surrounded by air can be found by the following formula. Here, maximum angle theta is said to be the acceptance angle. L is the distance between end of the fiber cable to the screen, and W is the width of the spot. Now let us see how the light propagates through this optical fiber. Let us consider an optical fiber with refractive index N1 as core and N2 as the refractive index of the cladding. Here N1 is greater than N2. Let N0 be the refractive index of the surrounding air medium. Typical size of the core is of the order of 50 microns in diameter, while the cladding size would be 2 to 3 times that of the core. The central dashed line indicates the axis of the fiber. Let a light ray incidence at the air core interface, making an angle θ1 with respect to this axis. After refraction, the light ray slightly bends towards the axis of the fiber in the denser medium, making an angle θ2. Now it incidents at core cladding juncture. In order to get this ray bounce back into the core, it needs to satisfy the condition that this angle must be greater than the critical angle θc. If this condition is satisfied, the incident ray propagates through the fiber and reaches the other end due to the total internal reflection. Let us now examine other case, where another ray happens to incident at the air core interface, making some other angle which is now higher than that of the previous incident angle θ1. This ray also incidents at the core cladding interface, but now making some other angle which is less than critical angle. As the total internal reflection condition is violated, this ray eventually lost by radiating out of the fiber. It indicates that beyond a certain maximum angle, say theta max, the condition of total internal reflection is violated. Thus, the maximum angle at or below which the light ray undergoes the total internal reflection to propagate through the optical fiber is known as the acceptance angle. Let us exaggerate the emerging out ray. It forms a circle of diameter W at a distance L. Let theta max be the maximum angle made with respect to the axis. From this right angle triangle, sine of the maximum angle theta is equal to opposite side by hypotenuse, where opposite side is half of the width and hypotenuse is square root of length square plus half of the width square. This upon simplification we get sine theta maximum is equal to W by under root 4 L square plus W square. This sine of the maximum angle theta when multiplied with the refractive index of the medium, here the surrounding medium is air, which is equal to 1, this product is known as numerical aperture. Thus, the numerical aperture of an optical fiber is its light gathering capacity. Acceptance angle is the maximum angle at which the light rays undergo total internal reflection within the optical fiber to reach the other side. Here, the maximum of the incident angle theta max is the acceptance angle. If we see this incident ray in 3 dimensions, the locus of the maximum angle traverses a cone. All the light rays which fall within this cone can propagate through the fiber. Thus, this cone is known as acceptance cone. Now let us see how to perform the experiment. This is the fiber optic trainer module. Light can be generated by turning on this button to on mode. The intensity of the output light can be controlled by turning this knob. Behind the board there is a PN junction diode based LED setup. If we see a little closely this setup, this particular LED generates 660 nanometer wavelength, which lies in the red colored region of the optical spectrum. One end of the optical fiber is connected to the output. The necessary components required to carry the experiment are labeled here. Now let us first of all assemble the setup. One of the ends of the optical fiber is connected here and fasten the screw. The other end of the optical fiber is connected to the scale. I am placing the measuring jig near to the scale. Now let us see how to control the output light intensity. If you turn the knob clockwise, the output light becomes brighter. Upon turning the knob opposite, it becomes dimmer. Let us keep the output light at its maximum level to get the maximum intensity. By moving the measuring jig forward or backward, the output light can be made to coincide with one of these concentric circles. Let us now check how to take the readings. By moving the jig slightly outside, I am making the light to fill second concentric circle. Now note the reading on the scale. Similarly, let me go for the next concentric circles and take the respective readings on the scale. The readings what I got here are 0.4 centimeters for the first circle, whose width is 0.5 centimeters. From the formula, numerical aperture is given by length by under root 4 times length square plus width square. Upon calculation, this value turns out to be 0.53, and the acceptance angle is sine inverse of numerical aperture. This value comes out as 32 degrees. The second reading for the next circle is found to be 0.9 centimeters. Its width is 1 centimeter. Using the same formula, numerical aperture is found to be 0.49, and similarly the acceptance angle is 29.3 degrees. For the next concentric circle, the length L is found to be 1.3 centimeters on the scale, and its width is 1.5 centimeters. Correspondingly, the numerical aperture is 0.5. Acceptance angle is 30 degrees. For the next concentric circle, length L is 1.7 centimeters, whose width is 2 centimeters. Its numerical aperture is 0.51 and corresponding acceptance angle is 30.6 degrees. If we find the average of all numerical aperture values, we get 0.51. Similarly, the average acceptance angle of all these values is found to be 30.5 degrees. Finally, the numerical aperture is found to be 0.51 and corresponding acceptance angle is 30.5 degrees. These values are tabulated and shown here. For the first interior circle, whose diameter is 0.5 centimeters, the distance of the screen is found to be 0.4 centimeters. Thus, the numerical aperture and the acceptance angle are found to be 0.53 and 32 degrees respectively. Similarly, for the second, third and fourth concentric circles, the values are shown here. Finally, the numerical aperture of the given optical fiber is found to be 0.51 and corresponding acceptance angle is 30.5 degrees. Following precautions are to be kept in mind before performing the experiment. Too much bending of the fiber renders losses. Thus, don't bend the optical fiber too much. As the source of light is very important here, handle it carefully. While taking the readings, see that the light fills the measuring circle entirely. Finally, thank you for your patience.